Hi, my name is Toby O'Geen. I'm a professor and soil resource specialist in cooperative extension. Today I'm going to talk to you about streamflow generation in California rangelands. My expertise is in soil-landscape relationships, so today I'm going to give you a soils perspective on how they influence water quality, streamflow, and hopefully direct management. The focus of my talk is going to be in California oak woodlands in the rangelands. This is a really important area in the state because it's such a vast land area, occupying about 3 million hectares across California. This is the ag-urban wildland interface, so there's a lot of pressures on these landscapes. And from a water quality and supply perspective, it's really important how we manage these landscapes because over 2/3 of all drinking water reservoirs are stored in these landscapes, and much of the water that is fed from the Sierras passes through these landscapes. So that's important to understand how our management influences the water quality and supply in California rangelands. So the focus of my talk today is going to be focused on hydrologic flow paths, understanding how soil stratigraphy and topography interplay to generate stream flow and how that might have an impact on water quality. And so what we've done is we've established an experimental monitoring catchment and paired watersheds. We have done detailed level of soil stratigraphic analysis, looked at over 100 soil profiles in this 30-hectare catchment. The catchment contains over 100 soil moisture monitoring sensors to understand how water is changing through time. It has a detailed assessment of the topography, the digital elevation surface of that catchment, so we understand all the micro landforms and landscapes associated with it. And so we're just trying to understand how topography, which is long beheld as an explaining variable of streamflow, relates with the stratigraphy of soils in guiding streamflow. So this is a typical soil profile that we would expect at that catchment. It's characteristic in that it has what we call a biomantle, this highly mixed layer that is at the soil surface, consisting of what we call A and B horizons. This is a very permeable layer, tends to be about 20 to 40 centimeters thick, relatively moderate clay contents, and conducts water very readily because of its porosity. Below that layer, we call a BT layer or a clay layer, slightly higher clay content, about 20 to 44%. Its permeability is lower, indicated by the KSAT. It is about an order of magnitude lower than the biomantle, and it has a variable thickness, so slight differences with depth. Below that layer is what we call a BTSS layer, or also called a claypan, and this is defined as a large clay increase, about 15%, over a very short vertical distance, less than a centimeter. And so that abrupt change in clay creates very, very different pore size continuity, and that slows the vertical percolation of water. The KSAT, or saturated hydraulic conductivity of this layer, is even orders of magnitude lower than the layer above it. And so that layer acts as a barrier to infiltrating water. And so effectively what happens is all water moves through the profile, percolating downward. It hits this clay pan right about here and essentially stops. And as more rainfall comes, it builds saturation upwards above that layer. And so how these soils are essentially constructed in space gives us an example of where water is moving through the landscape. So the continuity of that clay pan and the connectivity of it really helps us understand where water is being guided through the catchment. And so it's not just the topography, we feel, that's influencing where and how water moves through the landscape. So as I mentioned, we have this experimental catchment, and we are monitoring stream flow with partial flumes and V-notch weirs for low flows. We have a high resolution digital elevation model to characterize the different landforms in the catchment. We have over 100 soil profiles that have been described, characterized, and each of those profiles has up to 4 or 5 soil moisture sensors. So we're looking at how soil moisture changes in each one of these profiles through time in summer, winter, and fall, and spring. And then we have our perched water collection system located here. This is essentially a trench that has 3 soil profiles fitted with these collection trays that collect subsurface lateral flow or perched water as it builds through a storm event. And then it's routed through these tubes into tipping buckets located here, which record the flow rate. And we can also sample the water from those tipping buckets to get an idea of what the water quality is like. So this is just a hydrograph showing you rainfall at the top and stream flow at the bottom over time from the water year of 2006, beginning in 2006 to 2009. And so what you can notice here is, first of all, it takes some time, some rainfall to occur before we get stream flow. It's about 7 inches of rain has to fall in the autumn to fill up those soil profiles, fill the water deficit that occurred during the spring, summer, and fall months to allow those soils to reach saturation. And so once those soils are saturated, then they're subject, the water in the pore space is subject to gravitational flow, meaning there's nothing holding on to it, and it is just released with the direction of gravity. And if there's sloping landscapes, that's usually downslope. So it takes some time, some rainfall to fill those soils up. And then what you can notice in the streamflow hydrograph below, you can see that streamflow events in this landscape is highly ephemeral. In many cases, maybe we had 6 to even 3 streamflow events in each winter. These tended to be drier years. In wet years, we might see more prolonged streamflow events, but they are flashy systems. These are ephemeral streams, so they do dry out in between storm events if we're having a moderate to dry year. And so what we wanted to do is try to understand the linkage between stream flow and subsurface lateral flow in soils. And so here we have 2 graphs. The upper graph shows stream flow in a typical storm. The lower graph shows perched water flow, or subsurface lateral flow, we call it, in the lower graph. And we have flow coming from the different layers, the A horizon and the AB horizon. That's our biomantle, that highly permeable layer. The clay layer, which is green, and then just above the clay pan, which is in blue. And so first of all, what you notice is the timing of stream flow corresponds almost exactly with the timing of subsurface lateral flow in the lower part of the biomantle. There's a lag between the timing of flow in the other soil horizons with that of stream flow, and that's because in the lower horizons, they're much more slowly permeable because they have higher clay content, and so they conduct water more slowly. And the upper horizon, which is in black, is slower because it takes time for water to migrate above the clay pan up, saturating upwards towards the soil surface. So it saturates more slowly as the storm progresses in time. So what we discovered by looking at the combination of stream flow and subsurface lateral flow through these various storm events is that a bulk of the stream flow is coming from the biomantle, the A and AB horizons, the top uppermost soil layers. These are the layers that are most permeable. And so about 73% of all stream flow is coming from those upper layers. A lesser amount, 17%, is coming from what we call the BT1 horizon, which is located just right here, just above the clay pan. This layer is saturated for a very long time, even longer than the layers above it, but it doesn't contribute as much stream flow to the stream flow, and that's because it is, again, slowly permeable because of the higher clay content. So again, just to summarize what happens, rain falls on the landscape. It moves downward through the soils, percolating down, hitting this clay layer, or if that layer is absent, bedrock. These layers are very slowly permeable, so as more and more rain falls, the layers above it become saturated, and that saturated layer grows as long as rainfall continues to fall. And it grows upward until it hits these more permeable layers, and when they become saturated, they are subject to gravitational flow, and they flow with the direction of slope, or the stratigraphy, how those layers are pointing across the landscape. This is just some information showing you how soil moisture changes in these layers through time. Across the bottom of this graph, this hydrograph, we're seeing precipitation. And then these different colored lines are showing you soil moisture through time in the different layers. The aqua blue and black are the biomantle, upper and lower biomantle. The navy blue is the clayey layer, which is slightly permeable. The green is the claypan, and the red is a layer just below the claypan. And so what this is showing you is just a little bit of what we've already discussed. What you see is that the upper layers, the blue and black, are very dynamic in time. They are flashy, a lot like the stream. You see peaks going up and then crashes as the rainfall ceases. And that lasts throughout the year. During the storm events even, you'll see that they have a very flashy characteristic curve to them. And then once rainfall begins to dissipate and evapotranspiration kicks in, you'll see that there's a dry down, and then there's a summer drought, and then it all starts over again. In contrast, the lower layers, the navy blue, the green, and the red, show a more stable signature, meaning that they don't necessarily respond to precipitation early on in the season because that water is being absorbed by upper layers, but they quickly, once enough rainfall is fallen, maybe about 7.5 inches, they become readily saturated, shooting up to about 40% available water. And then they remain relatively constant in their saturation. You can see the relatively flat lines here. These layers are so slowly permeable, but they don't give up their water that easily. And so they tend to stay saturated unless you have a dry spell that lasts several weeks. And then they begin to dry down once water is being utilized by the trees and the grasses. And so those lower layers behave hydrologically very different than the upper layers, and it kind of supports what we've been describing about the flashiness of the streams, the flashiness and water content of the upper layers, and how the upper layers are responsible for much of the stream flow in these landscapes. So this is just a map showing you the distribution of soil water content during peak stream flow event in 2008. And so anything in green is essentially saturated, and then the yellow colors are not quite saturated. The lines that you see across these kind of flow lines that you see throughout the experimental catchment, the density of these lines correspond to how topography would influence the routing of water. The more lines you see in a given area, the more contributing area, or the more focused the water could be by topographic effects. And the take-home message with this map here is that you'll see areas of saturation, dark or green, that don't necessarily correspond with high focusing of water by topography. Here it does, but over here it doesn't. We see that the soils are not saturated and there's a lot of focusing. Also here we see that the soils are saturated, but there's not a lot of topography that's focusing water. Same with here and even throughout here. And so what this is telling us is that, yes, topography plays an important role in focusing water, and that at the lower parts of the landscape, we see a lot more wetness, which is understandable. But we also see that the spatial distribution of saturation appears to be related to some other things besides topography. And we would argue that this is the soil stratigraphic relationships. And if you'll see in this next map, go back real quick, show you what the spatial organization of saturation in green is, and compare that to the spatial organization of claypans. Soils with claypans are in dark blue, soils without claypans are in green. And you can, if you go back again, you can kind of see that there are some patterns to the spatial distribution of claypans and that of the degree of saturation in the soil. So what I'm saying here is that the spatial organization of saturated soil conditions is both an influence of the topography focusing water and also the distribution of claypans in the landscape, which perch water. So connectivity of saturated conditions is really important to get a feeling for how much water is being supplied to the streams. And so this graph up here is showing an example of connectivity of the different layers in terms of their degree of saturation. First of all, this upper line here in black is stream flow. The colored lines represent duration of saturation of different layers. How long this soil, if it is continuously purple, the claypan, means that the claypan was saturated throughout this time in purple. The green line refers to that clay layer that is right above the claypan, and this green, continuous green bar indicates that it was saturated continuously throughout that stream flow event, and even beyond that stream flow event, both these layers. The red and the blue represent the timing of saturation in the biomantle, the lower biomantle and the upper biomantle. And so again, what it's showing you is that between these 2 points, 2 and 3 on the landscape, these lower layers are saturated. They should be conducting water as stream flow, but you see they're saturated before stream flow occurs and they're saturated after stream flow ends. So really these layers aren't playing a big role in feeding the stream flow besides just perching water above them. It's these upper layers, the biomantle, that stay saturated only during the stream flow event, which are supplying the flow. And the AB horizon extending beyond the peak of the stream flow event here is clearly supplying a lot of the base flow to this stream. The peaks are strongly correlated with the saturated conditions in the uppermost layer. So this figure below is showing our best understanding of the stratigraphy of the soils across the catchment. We dug a trench from the upper part of the landscape all the way to the stream, and we carefully characterized the soils. And what we found is that the connectivity of the claypan is highly irregular. The connectivity of the biomantle in black is very uniform. It changes in thickness across the landscape, but very uniform. The kind of sandy colored speckled layer below the biomantle is that BT horizon in green bar, sorry. And then the claypan, you'll see in kind of a white checkered area here, is very patchy, showing up in only certain locations along the watershed here in white. And then gray is weathered bedrock and dark gray is hard bedrock. And so what this is showing us is that the irregularity in topography of the claypan, also the hard bedrock, these layers are going to perch water, and if there's enough rainfall, when it reaches these upper layers, it's going to go down slope. And so it's really important, the magnitude of saturation across this landscape, the magnitude of water that is fed to the stream is highly dependent on the degree of saturation of this black layer all through the landscape. Extremely wet winters will fill all these voids, allowing water to reach the upper layer and move downwards with the slope. Drier years, all this soil volume needs to be filled. In many cases, it isn't. And this irregularity in topography kind of creates little micro dams or reservoirs, which prevent water essentially from reaching the lower parts of the landscape, because you have to fill up all this thickness before it reaches that most conductive layer. So the point is that the nature of thickness of permeable material in soil is really important to understanding how much water is feeding a stream, and that will differ over time depending on drier years versus wetter years. In wetter years, it probably doesn't matter. Everything is fully recharged, and once that is the case, a little bit of additional rainfall will send water downslope. But in moderate to drier years, maybe only small portions of the landscape are fully recharged and delivering water to that upper layer, which will feed the stream. And so in drier years, you might be able to manage those landscapes more creatively and effectively to limit traffic or any kind of disturbance that might influence water quality coming from those landscapes. But you really need to know your soils to make that practice real or effective. So as I said, the effective soil depth is probably the most important characteristic in describing how long and how high streams will run. And effective depth is essentially the thickness of soil above a claypan, which is located right here, or some other water-restrictive layer, such as hard bedrock. And so understanding its variability in space is very helpful in knowing how your catchment will respond or will drive stream flow. So this figure is trying to make the connection between the nature and properties of soil and how they feed stream flow and how saturation occurs in these different layers with water quality. Dissolved organic carbon is one water quality indicator. It reacts with chlorine in the drinking water purification process and can form a disinfection byproduct that is carcinogenic. And so we don't like to see a lot of dissolved organic carbon in our water. And in this graph, you'll see in navy blue, this is dissolved organic carbon in soil in the subsurface lateral flow. In the upper part of the biomantle, the lower part of the biomantle, the clay layer below the biomantle, and in the layer below the clay pan. Here we see dissolved organic carbon in stream flow. The base flow, the initiation right at the beginning of a storm. As that stream begins to increase in flow, it's rising limb, it builds to a peak flow event. And then as rainfall slows or stops, the stream begins to go down, stream flow goes down to the falling limb, and then it reaches a steady state again at base flow. And so what we see here is that at peak flow and even in the rising limbs and falling limbs, when that stream is really gaining energy and flow velocity from the storm, its concentrations of dissolved organic carbon are relatively high, and those concentrations are very similar to that of the A and AB horizons, that of in the biomantle. The base flow, which is lower in dissolved organic carbon content, is more of an integration of all of these horizons, an average, if you will, of all four horizons. And so it has lower organic carbon concentrations. So this could be very helpful information to understand for water managers who might be taking water or not, allowing water to be excluded in the reservoir, or releasing water from reservoir during storm events, because at peak flow in the stream is when we are exporting the most dissolved organic carbon, and that's because it's coming from the upper layers of soil, which are higher in organic matter to begin with. So we wanted to help understand or use this information and use our monitoring network to evaluate rangeland management practices and how these rangeland management practices might influence water quality. And what we did at the same property is we compared water quality from our experimental watershed, which is what we're calling the control, which had no grazing for 10 years, with other paired watersheds of similar size and similar soils on this property. The one adjacent watershed had moderate grazing for 10 years at a moderate residual dry matter recommendation of 1,000 pounds per acre. We had another paired watershed that also had moderate grazing for 10 years, same RDM, but also had a prescribed fire event in 2004. So we wanted to evaluate, see if the fire had any effects on water quality. And then we also had a heavily grazed watershed, which had a lower residual dry matter target of 500 pounds per acre for 10 years. And so we wanted to compare the water quality at these different catchments to evaluate what the best grazing strategy might be. And so we looked at a variety of water quality contaminants. First, I'm going to show you dissolved organic carbon. Again, in the control, no grazing, moderate with fire, and heavily grazed. And what you see here is that there's no real difference in dissolved organic carbon in the heavily grazed or the moderately grazed watersheds, but we do see more elevated dissolved organic carbon in the control where there's no grazing. That makes sense. There's much more vegetative residue on these landscapes because it's not being removed or processed by the cattle, and therefore there's more source of organic matter in the soils that is available to flow through the pore water and into streams. So in this scenario, some level of grazing is actually important in managing the vegetation so that we can minimize the export of dissolved organic carbon into our streams. Here we're looking at nitrate nitrogen in the same paired watersheds, controlled, moderately grazed, grazing with prescribed fire, and heavily grazed. And first of all, what to notice is that with nitrate concentration across the y-axis, nitrate in this landscape is exceptionally low. The drinking water quality standard is 10 milligrams per liter of nitrate nitrogen, and in our heavily grazed system, we're not even reaching 1. So nitrate is very low in these landscapes, and it tends to increase with grazing. There's no difference between moderate grazing and moderate grazing with fire. So we do see an effect of the heavier grazing, but the absolute concentration is still quite low. Same experimental design. In this case, we're showing you the effects of grazing on total suspended solids, so the amount of sediment that is in streams. And again, we see relatively low amounts of total suspended sediment in the control, in the moderate grazing, and in the grazing with fire. And we see much higher concentrations of sediment in the heavily grazed catchment. This is an effect of removing cover. As we remove cover through grazing, there is less material, vegetative material, to protect the soil surface from the impact of raindrops. The raindrops fall on the soil surface, dislodge soil particles, and move them as surface runoff into the streams. But again, this concentration is fairly low. And that's an artifact of these soils. And if you notice, these soils are very red. There are iron oxides in these soils, which strongly aggregate those soils, making them more resistant to transport by water. And so in this landscape, we tend to see low total suspended solids overall, but an increase in the heavily grazed systems. And finally, we looked at pathogens and to see how grazing influenced fecal coliform and E. coli. And the unit that we're looking at are colony-forming units per 100 milliliters of water. And what you'll see here is the kind of the same story for the last two graphs, in that we don't see a huge difference in E. coli or fecal coliforms, E. coli in dark, almost black, and fecal coliforms in blue. We don't really see much of a difference. We do see a slight spike in the moderately grazed catchment that had prescribed fire, maybe because there is less cover. But then we see quite a large peak in pathogens in the heavily grazed system. And that's probably because there is more fecal material on those landscapes for a longer period of time, and also potentially because there's less vegetative cover on those landscapes, which act as a natural buffer to intercept those pathogens as they might be moving through runoff across the landscape. Interestingly, though, you see this red dotted line. This represents the drinking water quality standard of 126 colony-forming units. So what this is saying is that even with no grazing, we can't obtain that drinking water quality standard. There's a background of naturally occurring fecal coliform and E. coli that exists in these landscapes. And no matter what management we choose, we will never reach that target. So thank you for listening. If you want to learn more about the scientific content in this presentation, please take a look at some of these papers that we've published. And I'd also like to thank all the researchers who I've collaborated with over the last 10 to 15 years. Thank you.
You can find more informative presentations covering ranch water quality topics on the UC Rangelands website, and look for the Water Quality Information Hub or direct your web browser to the URL shown on this slide.